Okay, so I would like to talk a little bit about what's coming for roughly the next months of the course. So we already saw that languages are of interest to us, right? Because the question of whether a word belongs to a language or not can be described as essentially the most basic computational task. And it's mathematically a very pure question, right? We don't have to worry about various technicalities of how to read the input, write the input, and so on. It's all very abstract. And we already saw finite languages, and we already saw that they're easy. So the rest of the semester, large fraction of it, we will spend about various classes of languages and essentially a hierarchy of where the languages are. And just above regular finite languages, there are regular languages. Regular languages are quite interesting because they are very simple and yet very interesting. So in regular languages, there will be several equivalent ways to describe them. And somehow we need all those different ways to describe them to completely capture what can be done with those languages. So the first description is regular expressions, right? Which are, if you want, an extended search patterns. Some editors support it if you ever encountered it before. And then above that, we will speak about DFA, which is the deterministic finite automatas. The way to think about it, those are computers, maybe the simplest computer one can think of, that have finite memory, right? So you're not allowed to have counters that can count to infinity, everything. Here, really, the program has a bounded number of bits, 24 bits. What can you do with the program that they give you only 24 bits? And the next description is using NFA, which is just non-deterministic finite automata. And the way to think about NFAs is that it's automatas where there is limited memory, but you're allowed to make choices. The algorithm has free will to make choices. That's the non-determinism. Another way of thinking about it is that the finite automata can fork itself, right, and run on these parallel universes. And if in one of those parallel universes it accepts the language, then it accepts the input. And after we will discuss those three different models, which would be very useful to learn various properties of language, right? How they're closed down, their complement, union, star, and so on. It would be interesting to try and understand what languages are no longer regular. And the intuition behind non-regular languages is that non-regular languages are languages where you need a counter to recognize them, right? You really need to count something, and this counter can get arbitrarily large, right? And I already mentioned, I think, maybe the language A and B to the n, right? All the words where, it's a sequence of A followed by a sequence of B, and the number of A's and B's is equal. Clearly, any program that needs to recognize this language needs to count the A, right? And then count the B or subtract the count. And this you cannot do with regular languages. So the intuition is clear, but it turns out to be quite more complicated to formalize it. Then we will climb up, right? Then we will ask, what happens if I allow you a stack, right? So you still have finite memory, but you can push things and pop stick from the stack. And then you get the so-called context-free languages or context-free grammars, which are already quite powerful and used quite widely, by the way, both in natural language processing and in compilers and a lot of other places, because they enable us to describe hierarchical structure in a language, which is really important. And then the next step would be to speak about Turing machines. And, as I maybe hinted about earlier, Turing machines are just, for us, programs, regular programs. It turns out that another way of thinking about it is that Turing machines are just DFAs where you have two stacks instead of one stack. Somehow, just having two stacks is already enough to have a general computer, which is kind of amazing. And we will speak about decidable languages. Those are languages for which a Turing machine, given an input, can run and tell us whether the word is in the language or not, right? And surprisingly, we will show that there are things that are undecidable, right? In particular, there is the famous halting theorem of Turing that shows that given a program, deciding whether the program is correct or not, or whether it's going to stop or not, is undecidable, which is, very surprising. And that was Turing, fundamental result in the 30s. And then we're going to go even further, and we will speak about languages that are not even decidable, that are recognizable languages and unrecognizable languages and so on. And that's the plan of attack for, as I said, for the following months. And that's it for now.